Okay, let's go ahead and get started here. Can you hear me in the back of the room? All right, good. So we are here, November, not yet, September 4th. I want to point out for those of you who haven't been paying attention, there's a homework due in 1 week, okay? And that should be turned in online using B courses. Any medium that is legible is fine. PDF files are probably preferred, but whatever works for you, we'll accept. Any questions? Okay, good. One little announcement. The Tuesday lab people didn't get their account assignments, as you know. We have those here, so you can see Ben after class over here to get your accounts. Okay. So just a little bit of explanation of the order in which we're doing things here. We're front-loading the class a bit with content that is a little bit nitty-gritty embedded systems content deliberately because it aligns best with the labs. Because one of the things that we're trying to do in these first few weeks of the lab is give you experience with design of systems at 3 different levels of abstraction. Okay? The lowest level of abstraction is where you're really directly working with the hardware. There's no operating system in the way. So you've really got to understand how software interacts with hardware. And one of the goals is to make sure that you do understand that because that's an important part of designing interesting embedded systems. The second level, of course, is much more familiar to most people, which is where you're interacting through an operating system with the hardware. And there, the twist in embedded systems is that you care about the timing of things in a much deeper and more integrated way than you do with general-purpose computing, where timing is just a performance metric. In the case of many embedded system applications, timing is a correctness criterion, not just a performance metric. And then the third level is model-based design. And in my view, model-based design is still a somewhat immature area that is somewhat in flux, right? But there's technology that's improving very rapidly where engineers are using models at much higher levels of abstraction than the low-level software to design and analyze systems. So that's the goal in the first few weeks of the lab, is to give you experience and a little bit of experimentation with the trade-off between those levels. So as a consequence, in the lectures, we've kind of front-loaded with content that is much more on the design part of the course. If you remember, we showed that there's kind of 3 concurrent paths in this course: design, modeling, and analysis. And we're focused initially on design, which is why we're already on chapter 9. Okay, of the book. Okay, all right. So hopefully that helps understand the trajectory. So today I'm specifically going to focus on memory architectures because the issue is that memory looms larger for embedded systems as a problem than it does in general-purpose computing. In fact, a lot of computing infrastructure is very carefully designed to make you think that you have an infinite amount of memory, and you don't really care how long it takes to get anything. It's all going to be fast enough. Okay, that's how laptops are designed, right? That's the intent. That's their goal, is to make it seem that way to you. But in the case of embedded systems, it's very often not the case that. Well, first of all, you have to grapple with the fact that you don't have an infinite amount of memory, okay? You also have to, one interesting twist with embedded systems is that you care a lot about how the system behaves over very long periods of time. There's lots of embedded systems where rebooting is unacceptable and you want to run for years, okay? So you can't afford to just, keep allocating memory and never deallocating it, okay? That doesn't actually work because it'll cause your system to crash at some point. So a few of the issues that we're going to look at are, types of memory. What does it mean to have volatile versus non-volatile memories? What are the consequences of that? How does the logical address space for memory relate to the physical address space. Where is stuff stored, and how are you getting to it? Okay, is the issue there. How memory is organized. So in particular, when you run a program, are your variables being stored at a location that the compiler decides that's just fixed for the whole duration of the execution of the program? We call that statically allocated memory. Or does the variable live only in memory for the duration of a procedure call? That's a variable that's allocated on the stack. Or does the memory get allocated temporarily and then explicitly deallocated, where your software has to say, well, I no longer need this variable. You can now use this memory location for something else. Okay, we call that the heap. So these are three very different ways of dealing with memory, and in embedded systems, you really have to pay attention to what you're doing with your memory. So that's going to be a big part of the focus today. And we're going to focus on the programming language C, which provides a particular access to these memory models. Now, the reason for focusing on C is that, unlike most modern languages, C gives you very direct control of the hardware. Okay? Now, if you run a C program on your laptop, there's an operating system and some hardware in the way that will actually prevent you from doing a lot of stuff that you actually would like to do. So you can't necessarily access all physical memory locations. You sort of need the operating system's permission. You have to go into kernel mode to be able to access certain locations. But in the embedded systems context, often there's no kernel. There's no operating system. You control the hardware, and you can do damage. But you can also do wonderful things. And so you're really controlling the hardware. And so we need you to kind of understand how that works. Okay, so let's dive right into this. So volatility. A lot of the memory that we deal with, if it loses power, it loses data. Okay, we call that volatile memory. Non-volatile memory has been around for a long time. I actually used, when I was in college, these memory devices. That chip up there is under a quartz cover. It's quartz, not glass, because it needs to be transparent to ultraviolet light. And you had to stick it in this little oven. It's not an oven, it's actually just a UV light, but it was enclosed because you don't want people getting sunburned. And leave it in there for a few minutes, and everything would be erased. And then you could plug it back into your circuit and start writing data to it, okay? And you could write once. And if once you had written to a location, the only way you could write again to that location was to pry it out of your circuit board and stick it back in that oven to erase the contents, okay? So that was called an EEPROM, an erasable programmable read-only memory. Shortly thereafter, an EEPROM was invented, where you didn't have to pry it out of the circuit board and stick it in an oven to erase it. You could actually erase it electrically. But that seems great, except that it was the only part of your circuit that required 24 volts. So you needed an extra power supply in order to be able to erase your memory, because everything else was running off of 5 volts. So that was a hassle. Flash memory has been around for quite a while. It was actually invented in 1980 by a fellow at Toshiba. And it's prevalent now. Many of you probably have laptops that don't have disk drives, that you're using flash memory instead. And flash memory is actually creates a very interesting engineering problem, because you can't just overwrite a location, a single variable. You actually have to erase a block of memory and then overwrite that, okay? And in addition, you have a limited number of times you can do that. With today's modern flash memories, you can overwrite each location about 100,000 times. So think about that when you're using your laptop and you delete that video and replace it with another video. Well, you've got a limited number of times you can do that. Okay? Now, hopefully, I guess the controllers for these things are actually trying to optimize so that your whole memory will fail all at once, right? So they're actually remapping the memory continually to try to keep it balanced so that the rewrites are occurring across the whole memory, which creates a very interesting control problem. In fact, I've been to conferences. There's one conference that I go to every year where literally 1/3 of the conference every year is devoted to research papers on managing flash memories. Okay, and there's all kinds of optimizations you can do if you're interested in operations research, right? And the optimization problems that they do, there's a good application for them, flash memories. Disk drives, of course, are also prevalent. This guy has a disk drive because I need a lot of space, and the flash memories that are available on these are not enough yet. But they're somewhat more problematic for embedded systems because they have a significant mechanical component, and if that has size, power, and reliability implications. So those are all non-volatile in the sense that you remove power, the data stays there. Okay, volatile memories, if they lose power, they lose data, and in fact, dynamic RAMs can lose data even if they still have power. In fact, dynamic RAMs are essentially capacitors controlled by a single transistor, and there's leakage, and they forget. Okay, and they will forget if they're not refreshed. And in fact, each memory location in a dynamic RAM needs to be refreshed approximately every 64 milliseconds. Okay, so that's roughly 15 times a second. Okay, so 15 times a second, every single location in the 4 gigabytes of dynamic RAM on this device gets rewritten. Okay, 15 times a second, and if it fails to get rewritten, it's going to forget. So dynamic RAM is particularly volatile memory, and it also has the property that you have to sneak in those rewrites. The controller has to keep doing those rewrites no matter what your machine is doing, and often those rewrites will collide with whatever your software is doing, and your software just has to wait. So this creates an interesting timing problem because it means that you don't really know how long the memory access is going to take because you could be blocked by one of these refresh cycles, and that's going to introduce variability in the timing. In addition, with dynamic RAMs, the time that it takes to access a particular memory location depends on how long, on what address you accessed in the previous cycle. Okay, so the memories are very carefully designed. There's a lot of parallelism in them. So there's a bunch of separate memories. Okay, and if you read from this one, and then in the next cycle read from this one, and then in the next cycle read from this one, then things will go pretty fast. But if you read from this one, and then in the next cycle try to read from the same one, that second read is going to stall. And it's going to stall until the first read completes, which can actually be quite a few cycles, many cycles. Okay? Now, one of the conundrums that you face as an embedded software designer is you don't generally know how the memory addresses are mapped onto the physical memory. And on top of that, you don't know how your compiler is allocating memory unless you look at the output of the compiler, disassemble the assembly code, then you can look at how the memory all got allocated, and then you can tell. But who wants to do that? So you really have to dive in very deep into the software that the machine is actually running if you want to understand the timing of the memory accesses. So for practical reasons, that's rather difficult to do, which basically means that anytime you're accessing dynamic RAM, you don't know what the timing is going to be. And you're going to have to design your system as for worst case, all right? Which means that no matter how good your memory is in terms of being designed for average case, for laptop use, you're going to have to design your embedded system for worst case as if it was a really crappy memory, okay? So that's kind of a problem, right? I mean, in a sense, the memory designs are not well suited for embedded system applications. Static RAM is different. The access times are predictable, controllable, but it's a much more expensive memory technology. So in the circuits, a dynamic RAM is typically implemented with a single transistor today. Static RAMs are typically implemented with at least 6 transistors. So they're quite a bit bigger in area, which means that on a given region of the die, you can't have as much memory. Yes? Because the access actually takes a while, right? It takes several cycles to complete the access. And the circuit is busy while it's doing that. But if in the next cycle your address takes you to a different bank, okay, then that bank's circuit is not busy, right? So if your second address takes you to the same bank, then the circuitry will just block the request until the request that is currently going completes, okay? So it can be really very difficult to understand the timing. And, there's a whole cottage industry of people who make software tools that you can, give them the output of your C compiler, give them a very detailed model of your processor architecture, and they'll analyze the timing, okay? But that kind of timing analysis is extremely difficult, and in fact, we're going to talk about it towards the end of the semester. There's an introduction to that problem of timing analysis in Chapter 16 of the textbook, and we'll talk about it in more detail towards the end of this semester. It's a very sophisticated kind of analysis that you need to do. So one interesting thing that also you need to worry about with embedded systems that you kind of also need to worry about them with general purpose computers, but it's kind of taken care of for you, which is what happens when the power gets turned on, okay? Your volatile memory has garbage in it, right? It could start up in an arbitrary state, and the processor clock starts, and something's got to happen, right? If the clock is running on the processor, then the program counter is getting incremented, and memory is being fetched at the address specified by the program counter. So you turn on power, and the processor runs. It runs if there's power. It'll be clocking, and it'll be fetching whatever is in the program counter, which is a register, will be fetched and executed. Okay? So how do you get a processor started? Sorry? Right. Exactly. Exactly. Right. So as part of the power-up process, right, what will happen is the circuitry will initialize the program counter with a fixed address, say 0, okay? And the circuit will direct all memory requests to address 0 to a non-volatile memory, okay, that contains a hardwired program in it, and that program is what we call a bootloader. Okay, so typically that program is very simple. All it does is copy a bunch of stuff from another non-volatile memory, the flash, into the RAM, and then set the program counter to the beginning of that. Okay, and that's how things get started. So the big thing about flash, one of the reasons that flash took off as a non-volatile memory, is that it can be implemented with technologies, the same silicon technologies that are used to implement the processors. Okay, and the power supply requirements were the same as for the processors, so it's very convenient. So this is a die photograph of a fairly popular embedded systems processor, an ARM Cortex M3, which is a 32-bit microprocessor. And this has a megabyte of flash memory right on the chip. I believe the flash is that block at the top, and I think that down here this is dynamic RAM. Okay, and in the middle is the processor. You can recognize, if you're a circuits person, you can probably recognize a standard cell design in that central part of the chip. But, okay. Memory maps. For that particular... Oh, yes, question.
Why do you say that we cannot erase a specific location from the flash memory and we always use block bytes?
Actually, why do we say that? Well, because it's true, but why is it true? I'm actually not sure. Is there a circuits person who understands how flashes work and can explain why you have to erase them by block? I'm not really a circuits person, so I don't really understand the circuits of flash. But good question. Okay, so memory maps. So there's a lot of different ways for dealing with the problem of what to do with a memory address. Okay, the hardware and the processor. Yeah.
Sorry,
Gil.
question about refreshing dynamic memory.
Yeah.
Does the controller has any idea about which memory is currently damaged?
So the question is whether the controller has any idea of which part of the memory needs to be refreshed versus parts of the memory that are not actually being used and hence don't need to be refreshed. I don't think so. The controller that does the refresh is built into the hardware of the RAM chip. It has no... Yeah, I don't think it has any visibility into what the operating system is doing. So memory allocation is typically handled by the operating system, and so it's going to just refresh everything. Okay, so on this particular processor, here's how the memory map works. Now, one of the things I'd also like to point out, just to give you a sense of what I'm doing here, I'm going to be actually talking about a bunch of different processor architectures. Now, we could do this very differently because in the lab, you're working with two processor architectures, okay? One is an ARM and the other one is a microblaze. I could just show you those. But I don't want to do that because what I want you to get a sense of is sort of a pattern of how these things are designed and what the differences are between the low-end processors and the high-end processors. In embedded systems, you often want to put in processors that consume milliwatts or microwatts and only cost 15 cents in quantity, okay? Those aren't high-end Intel processors. They're quite different, okay? But we sometimes need more powerful processors in embedded systems, too. So you get the kind of whole range to work with. And I want to give you a sense of the wealth of possible choices that can be made across these different architecture designs. Okay, so this ARM processor is a 32-bit processor, and it has 32-bit addresses for memory. So what does it mean to have a 32-bit address? Well, it means you can address 2 to the 32 locations, which is 4 billion memory locations. Okay, 2 to the 32 is about 4 billion. So you have a 4 gigabyte memory space, okay? And the addresses are 32 bits, which we typically write in hex. So you'll get used to reading a lot of hex if you're not already used to it, right? But each symbol here represents 4 bits, okay? So there's a total of 32 bits here. And address 0 is pointing directly into flash memory, okay? Starting at address hex 20000, okay, you start addressing static RAM, okay, and you have half a gigabyte available of static RAM. Now, let me ask you this. Does this mean that if I give you an ARM Cortex M3, I just hand it to you, here's the chip, that there's a half a gigabyte of static RAM on it? Does not mean that at all, okay? There could be any amount of static RAM up to half a gigabyte. The memory map is a logical mapping, okay? It doesn't tell you anything about what is physical on the particular implementation. It also doesn't tell you if you have only say, 500 megabytes, those could be mapped anywhere in here. Okay? They might be at the bottom addresses, or they might be at the top. And your compiler is going to need to know, right? So the compiler has to be parametrized to know where there is memory, because if it writes to locations where there's no memory, then what do you think is going to happen when it reads back from those values? It's probably going to get zeros always, maybe, if the circuitry is designed that way, right? If you read from an address where there's no physical memory, carefully designed circuit would probably give you at least a predictable value, maybe just all zeros. But it's certainly not going to be the value you wrote to that memory location. Now, you don't see this problem when you write programs on your laptop, because the operating system and the compiler together make sure you never write to physical locations that don't exist. But when you're writing C program for a bare iron processor, you can write to any one of these addresses, okay? And the hardware will just do what you told it to do. Hardware is stupid. It does what you tell it to, okay? And if you tell it to do something stupid, it'll do something stupid quite happily, right? So you kind of have to know how this is going to map into physical space. So there's also this concept of memory mapped registers. So here's 0.5 gigabytes of potential locations that might be actually some other piece of hardware, some peripheral device, okay? Maybe it's an A to D converter at a particular memory location. So what it might mean is that when you read from a memory location in that range, you're not reading from memory at all. You're reading the latest value captured by an A to D converter, okay? That's a memory-mapped peripheral. Okay, so then there's 1 gigabyte available for dynamic RAM, another gigabyte for external devices, which could be memory also. You could hang other memory off of those external devices, and so forth. Okay, so that's how this particular architecture, this is an architecture, not an implementation. There are several chips that implement this architecture, and they could have varying amounts of memory. But the architecture tells you this logical mapping. Now let's look at an extreme that's at a different, oh yeah, question. Is not always what? Oh, right. So, okay, so what I said is that what this architecture tells you is that any address in here should refer to a location in static RAM, okay? But that's a constraint, not a requirement. You might not have that much static RAM on your implementation. Okay, whatever static RAM you have should be mapped somewhere into this address space. Okay, that's what that means. Yes.
This memory might be defined in hardware, or is it some software?
So this map is neither hardware nor software. This is documentation published by ARM. Okay, and if you're a chip designer, you can actually license from ARM this architecture and make your own ARM processor that conforms with this architecture. And when you make that, you're completely free to put your physical static RAM anywhere in this region. Okay? Sorry? Then you get hardware after that, right? But this isn't a description of hardware. This is a description of an architecture. Yes?
This is more like a convention.
This is the convention, or the requirements. Anything that calls itself an ARM Cortex-M3 needs to conform with this.
If it's a convention, it means I can maliciously not.
You could maliciously violate this, and you could play games. And in fact, actually, you can play lots of games with this, right? I mean, you can. Those external devices, well, what are they? Well, I could put static RAM on them, right? Yes? That's right. Seems kind of small, huh? I've got 16 gigabytes on this guy, right? But I do a lot of programming in Java, and that's really sloppy in its use of memory. So I need 16 gigabytes. Yeah.
In this case, if you need more memory, you can just say peripherals are memory, and the external devices are also memory.
You can do that. Yeah, you can map these external devices to memory as well. By the way, you will pay a price, right? Because it means that every compiler out there that is written for an ARM Cortex is going to have to be customized for your processor. Okay? Yes, Gil.
Okay, that's just a convention, but for I/O ports, are there any bounds or barriers to writing to I/O memory?
The question is whether there are bounds or barriers for writing to I/O memory, and the answer is no. The architecture doesn't impose any constraints. I've run across peripheral devices that are memory map devices, and they have you can write to a location, okay, that it refers to that device, and then read back from the same location, and what you read back is bit flipped from what you wrote. Okay. If you wrote 1111111 and then read it back, you'll get 00000. And if you wrote the reverse, it will flip the bits. Why they did that, I have no idea. But that's an implementation detail, yeah. But, I mean, an operating system needs to know that. So typically, the part of an operating system that knows this is what we call a device driver. So a device driver is simply a piece of code that writes to these memory map registers, reads from the memory map registers to determine what the status of the device is, okay? And the device driver is really what interacts. It's the bridge between your software and the peripheral device. Writing device drivers is tricky because you write them at the lowest level. You're directly controlling hardware, and you can make mistakes. And the most common causes of crashes, like this machine crashed 15 minutes ago when I plugged in the projector. Why? There's a flaw in the device driver, okay? I don't know what the flaw is. I'm hoping Apple will fix it. But there is a flaw in the device driver that's dealing with the writing to a memory-mapped peripheral, which is driving the display, okay? And it caused my machine to crash. Yes?
So you said that ARM gives you this architecture.
Right.
Any company which licenses out has to give this architecture. Let's assume that there's 500 MB instead of let's assume there's 125 MB instead of 0.5 GB of static RAM.
Right.
So this would mean that when I'm looking at this architecture, I'm assuming that it's 0.5 GB, but in reality there's only 125 MB.
Well, you can't assume there's 0.5 gigabytes. Think of this as a constraint, not a requirement, okay? So a particular implementation will have some amount of memory in it. And your compiler or whoever's writing the software has to know that.
So then the compiler would be dependent on the actual the person who's making the hardware as opposed to the architecture.
That's right. So if you play funny games with this, you're going to end up having to customize the compiler. Okay? That was my point before. Okay. So let's look at a lower level processor, an Atmel AVR. Okay? I really like these processors because they are, first of all, extremely cheap. I mean, literally, you can buy variants of this architecture that are 15 cents per chip in quantity. And they're very widely used. There are probably by a couple of orders of magnitude more of these processors in the wild than there are Intel processors, okay? Counting all the laptops and everything else, because they're in your microwave, they're in your watch, they're in all kinds of stuff, right? Very widespread. So it's an 8-bit single-chip microcontroller, was first developed by Atmel in 1996 based on an architecture that was developed by two students at the Norwegian Institute of Technology. And AVR is rumored to stand for Alf and Vigard's RISC processor. Okay? But no one, at least Atmel, will not officially confirm that that's the source of the term. They just say it's just an AVR. But anyway, Alf and Vigard developed this architecture, and Atmel picked it up and started making processors. By the way, 1996 seems like a long time ago, but the same thing is happening now here at Berkeley with the RISC-V, okay, which is a really nice architecture that was developed here at Berkeley that has been put in open source, and there's a bunch of implementations happening around it. So keep an eye on the RISC-V as an interesting architecture for the future. Okay, so one of the things that made the AVR take off is that it was one of the first microcontrollers that included an on-chip flash memory, which is extremely convenient because it meant that if you're building a microwave oven or something, one chip could handle the whole computing problem, okay? Including, you basically pre-configure it with the flash that contains the program, and it's a one-chip solution. And at 15 cents per chip, that's a pretty good buy. You can make some pretty cheap microwaves, okay? One of the very popular uses of AVRs these days among hobbyists is in the Arduino processors. And the Arduino is an open source board level architecture. So you can make your own Arduinos, okay? But a lot of the ones that you buy, if you want to buy it commercially, so if you buy this is the Arduino 2009. It's made in Italy, like my colleague Alberto. And it's a beautiful little piece of hardware. You can do all kinds of stuff with this, and it's a wonderful device for experimenting with. And probably quite a few of you in your projects will use Arduino processors. This is the processor here. It's in a 28-pin DIP. DIP is not referring to the personality of the person sitting next to you. It means dual inline package, right? It's 2 lines of pins, okay, is what a dual inline package is. And on this particular board, that's what they're using. They're not using a surface mount or solder connection. It's the dual inline package, so you can pry the chip out if you fry it and replace it with a new one, okay? So anyway, here's another use of the AVR processor. In fact, the first time we used the iRobots in the lab, which you'll be using in the lab, we used this particular processor, and it was an Atmega 168 made by Atmel, and it's an AVR processor. And one of the things I like about this processor, this particular instance of the processor, is that the amount of memory on this processor is measured in millibytes, not megabytes. It was tiny, okay? It had 1 kilobyte of RAM. 1 kilobyte. This has 16 gigabytes, okay? What do you do with 1 kilobyte of RAM? That's all it had, 1 kilobyte of RAM. It had 14 kilobytes of program memory. Not going to write any Java programs on that, right? You can't do Hello World with Java with less than, an order of magnitude more memory than that. So if you really want to get down and dirty and understand hardware, this is a really nice platform to program, okay? So let's look at it in a little more detail, all right? So this is the particular AVR that was used in this Atmega, and here's a diagram that comes from the Atmega 168 reference manual. And my hope is that, by the end of your lab experience with this course, you will be quite familiar and comfortable looking at these kinds of diagrams and kind of puzzling through how things work. By the way, let me tell you, stylistically, there's one thing we do to you in the lab that may seem a little surprising and shocking, right? We'll happily point you to a 500-page document and say, and then ask you a question about it, okay? And, if you approach this the way you would in other courses, you would go sit down in a comfortable chair and start on page 1 reading the 500-page document. It's not going to work, okay? So one of the things we're hoping to do is to, give you some experience with finding information from an overabundance of what's available, okay, and being able to zero in on the right place, right? And a lot of times these diagrams can be really helpful because they tell you a lot about what's going on. So this diagram, for example, right at the top, you probably can't read that in the back of the room, but it says that the data bus is 8 bits, okay? So the chunks of data that this processor deals with are 8-bit chunks of data. And in every instruction cycle, you're going to at most be able to operate on 8 bits of data. Doesn't mean you can't operate on a 32-bit integer. It just means it's going to take you several cycles to operate on a 32-bit integer because you can only do 8 bits at a time, okay? So it has 1 kilobyte of RAM right there, and it's static RAM. So the timing of this processor is actually very predictable. That's another thing I like about it. If you look at the assembly code, you can figure out the timing of all of the I/O operations by just counting instructions between the operations. Okay? Can't do that with a lot of other processors, right? But if you need really precise control over timing, these low-end processors are often a better choice than a high-performance, high-end processor because you can really control the timing. Okay? All right. So this also has a whole bunch of peripheral devices, and some of these we're going to talk about next week and show you how these memory-mapped I/O devices work, how timers work, and things like that, how interrupts work, etc. But we'll defer that until next week because today we're focused on the memory architecture. Okay. So one thing about this architecture, it's an 8-bit microcontroller, but it has 16-bit addresses, right? What if it only had 8-bit addresses? How much memory could it address? 256 bytes. Okay, that's even less than 1 kilobyte, which is what you have on this processor. So 8-bit addresses wouldn't be very useful. So 16-bit addresses still can't address a whole lot of memory, right? It's 2 to the 16th is about 64,000, right? So the fact that this processor only gives you 14 kilobytes of program memory, well, I mean, if you were to make a variant of this and max out the memory, you're still only going to get 64 kilobytes of memory because that's all that the processor can address. Okay? Any more than that doesn't work. Okay. So the 8-bit data is the reason why this is called an 8-bit microcontroller. Okay? Because it operates on 8-bit chunks of data. Now, here's a couple of questions. All right? So see if you've been paying attention. What's the difference between an 8-bit microcontroller and a 32-bit microcontroller? Someone want to tell me? Yes.
It's basically how much the memory addresses, how much memory to do with that address. So the 8-bit microcontroller can only address, or it can only address the addresses.
Nope. Yes.
The width of the data bus.
It's the width of the data bus. It's how much, the size of the data words that you're dealing with in each instruction. Okay? That's just a convention, by the way. You know, we could have easily had a different convention where this processor would be called a 16-bit microcontroller because it uses 16-bit addresses. But instead, by convention, when we say it's an 8-bit microcontroller, we're talking about the chunks of data that it operates on, not the chunks of address. Yeah?
Regarding mapping addresses, can't we just use more than one cycle without the address? We really want to.
Yeah, you could. So you could build peripheral hardware that could handle a bigger address space by, for example, giving the first half of the address in one cycle and the second half of the address in the next cycle. So you could definitely do that. Yeah. Yeah.
Talking about the width of the data bus, are you talking explicitly about the width of the data bus or the width of the ALU as well? Because like some processors do funny tricks. You know, like normally it prefers to work on 8-bit, but you can double pump it to, and the ALU can handle 16-bit.
Yeah, that's a very good point. And you know, I mean, any reduction to one word of something as complex as this is going to leave out a lot of detail, right? So if you hear that it's an 8-bit microcontroller, that tells you something, but not a whole lot, right? Well, so the convention would be that at least the inputs to the ALU are 8 bits, okay? but the output could be more, and often is, because if you add two 8-bit numbers and you want to avoid overflow, you actually need more than 8 bits, right? So it's conventionally it's common for the ALU to be wider on the output, but in this case, actually, you can tell from this diagram that it's not, because the output of the ALU goes to an 8-bit bus. So it's 8-bit inputs, 8-bit outputs. The diagram tells you that already. Yes? You can store long ints in memory. It's just going to take you several cycles. Right. So there's always this trade-off between time and resources, right? And if you have a lot of time, you can sequentialize things, right? So okay. So second question. So see whether you've been paying attention. Why would we use volatile memory? Why don't we just use non-volatile memory always? Let's hear from someone else, someone I haven't heard from. Yes, right there. What's your name? Yeah. Yeah, that's one big one, is that, the volatile memory, if flash memory, will wear out after a while. Okay, so DRAM doesn't wear out. Well, probably does. You get electromigration, but it really takes a long time to wear out. Yes? Volatile memory is also faster to access, especially static RAM. So don't get confused. Why is static RAM called static if it's volatile? No refresh, right? So there's sort of different levels of volatility. Volatile means if you take away the power, it forgets everything, okay? Yes? It's also cheaper. That's right. Dynamic RAM is incredibly cheap per bit, okay? All good reasons. All right. Yes? The first reason was that the flash memory in particular wears out after a certain number of accesses. You can only write to it so many times, and then it breaks down. You can only write typically about 100,000 times. So if you have a 2 gigahertz processor, you could wear out your flash memory in a small fraction of a second. Yes? Oh, yeah. I'm going to talk about that a little bit later on, so hold that question until we get to it. Okay, so let's talk about the memory organization for programs. And in particular, what I'm going to focus on is the distinction between statically allocated memory, a stack, and a heap. Okay? And the reason for focusing on these is that you really have to pay attention to these issues when you're writing low-level bare iron programming or writing device drivers, right? They matter a lot. Okay, so what do we mean by statically allocated memory in C? Well, here's a short C program, and here char is a data type that refers to an 8-bit quantity, okay? It's because it's an ASCII character, is 8 bits, okay? So x, the variable x, is being declared outside of any procedure call here, okay? So by definition in C, that is a statically allocated variable. So what that means is that the compiler chooses a memory location for that variable to live, and for the entire execution of the program, that variable x will be at that memory location. Okay? That's what that means, very precisely. So when I assign 0x20 to x, I'm writing an 8-bit quantity into that 8-bit location at that fixed location chosen by the compiler. Okay? Suppose that I wanted to write a program that tells me what address the compiler chose. How could I do that? Yeah. If I have a print statement, embedded processor, right? 15-cent chip, okay? Sitting on a board in your microwave. No print statement. Where's it going to go? Right? There's no screen connected to it. But if you have a print statement, okay, and some place to read the result, then you could precede the x with an ampersand, okay, and find out what address the compiler chose to put that variable at, okay? All right. This is also a static variable. What's the difference between this and this? Pretend you can't read this. I mean, it says so right on the slide, right? So from the perspective of the layout in memory, it's the same. The compiler chooses a location, okay? But the only difference is that when your C program compiles, if you refer to the variable x outside of this, the scope of this function, you'll either get a compile error or you'll get a different variable altogether, okay? But you can't reference this variable outside of that scope. But it's still going to be statically allocated, and it's still going to have its lifetime be the entire duration of the execution of the program. Yes, Gil? Oh, yeah. One of the beauties of C is if there's no operating system in your way, whatever protection this gives you is bogus, right? I mean, if you like the idea of writing viruses, C is the language to use. Yes, it's the same logical address. That's right. So really, this is a way. Doing this is a good idea because you can catch some programming errors. Okay, it helps the compiler to catch errors that you made, where you referenced X where you shouldn't have, or you referenced X, you thought you were referencing this, but you're actually referencing that, something like that. Okay? Yes? Right? Right. No, X will be allocated only once. And if you call foo twice, the second time you call it, X will still have the same value it had the first time you called it. So X is persistent across calls to foo in this case. Well, the compiler, the static is a keyword in C, and so the compiler recognizes that, oh yeah, this is something I need to just allocate a fixed memory location for once. By the way, there's one real trickiness that comes up in embedded systems, right? Which is in ANSI C, you can initialize the variable X, the static variable, to an initial value, okay? So when is that initial value put into memory? When is that initial value put into that memory location? When it runs is one conjecture, but usually not, actually. It's in the binary. So it's put into memory when the program is loaded. Okay? When your bootloader copies the program into memory, the initial value goes into the memory. Now what that means is that if you load your program into memory, and then you push the reset button to restart the program, it doesn't reinitialize the variable. Okay? That memory location will still have whatever the previous execution of the program had. That's a very interesting source of bugs. Okay? It means that when you push the reset button on your processor, it doesn't necessarily go to the same state it went to when you loaded the memory. Okay? Very tricky. Okay. So if you omit the static keyword here, then what that means is, first of all, logically, the variable X lives only during the one execution of this procedure. Okay? So memory will be allocated when you enter the procedure, and then it gets deallocated when you leave. Deallocated means that the memory location can now be used for something else. Okay? And this is done using a stack. Okay, so a stack is simply a pointer into memory. And when you call a procedure, what the compiler does is it inserts an instruction to increment the stack pointer in order to make room for that variable x. Okay? So, and then, if you have another variable, it'll increment the stack pointer again, and so forth, right? So the stack will be, on this particular processor, here's the memory map for this processor. So the bottom 32 addresses in this particular AVR processor refer to machine registers, okay? So the registers themselves are in the memory space. That's a little bit of an odd thing about ALF and vGuard's RISC, okay? Not all processors do that, but the AVRs map the registers into the memory space. So that means, by the way, one of those registers is the program counter, okay? If you accidentally write to a memory location that happens to be the program counter, what's going to happen? You're going to do a jump to whatever location you specified when you wrote into that address, okay? So the stack pointer will typically get initialized to the largest address of available memory. And then when you push something onto the stack pointer will get decremented. So the stack moves from the top of the memory down. What happens if you overflow your stack onto those I/O registers and the registers at the top? Well, you're going to write a bunch of junk to your I/O devices, right? Your motor controller, okay? Your PWM motor controller is going to get some random value because you overflowed your stack, okay? And then you're going to overwrite your program counter and start executing random data at some random location. This is not good, right? I mean, you can kill people this way, right? This is why you really got to pay attention to what's going on in the hardware. Yeah. Yeah, but you can't fit a shell interpreter in this 14 kilobytes of memory. There's no operating system here, right? So you're just directly controlling the hardware. Okay. All right. So let's see. So the stack will grow as shown in this little animation here, right? So there it is shrinking. There it is growing, right? And you have to be really careful to not overflow. Yeah.
There's some processors that have a sort of a DMZ inside of the RAM that will detect when something is written to it and trigger an interrupt so you can handle it.
Yeah, so higher-end processors have memory controllers that segment the memory and will actually trigger a hardware fault if your program accesses locations it shouldn't be accessing. Okay? In fact, how many of you have seen the message segmentation fault? What is that? Your program tried to access a memory location that it's not allowed to access, and the hardware caught it, right? And the hardware triggered an interrupt. We'll talk about how interrupts work next week, okay? And that interrupt aborted your program, which basically means resetting the stack pointer, okay? That's what it means to abort your program. You just reset the stack pointer to the top of memory, and you throw away the return address for your program, and you reset the program counter to start now executing your bootloader or whatever. Yeah. It could be a fault from the page mapper also. That's true. So the memory architectures get quite elaborate in higher-end processors. Okay, so I'm going to go through a series of questions here now, and I'm going to answer the first one for you, but I'm going to then pause on the second one, and I want someone to give me a good answer of it. And the goal here should be, when we pause, if you can answer the question in your head, then you've got a good understanding of this, and you've mastered much or most of Chapter 9, Chapter 10, whatever the chapter is that we're looking at. Okay, so the first question is what is meant by the following C code, and what it doesn't say a lot, right? But what is meant by it is that the compiler is going to allocate a static location to store 8 bits, okay? And when the foo procedure is invoked, we will write the 8-bit quantity hex 20 into that memory location. That's what that means, okay? So an 8-bit quantity, hex 0x20, is stored at an address in internal RAM determined by the compiler. So what is meant by this? So I want just a pause, okay? And I want a show of hands when you're confident you know what it means in the same spirit. There's a lot of you are not confident, right? It's okay not to be confident, so we'll walk you through it, right? But yeah, you want to? Right. Yeah, so here the difference is that X is a pointer, okay, which means how much memory is going to get allocated by the compiler? 16 bits, 2 bytes, right? Because it's a 16-bit address space. So the compiler is going to allocate 2 bytes at a location of its choice to the variable X, and then it's going to load it with what? 0020, right? So in C, by implication, this gets 0 filled, okay? And that's what's going to get loaded into that address. So a 16-bit quantity, 0x0020, is stored at an address in internal RAM determined by the compiler. Okay? Let's do the same exercise here. So what is meant by this program? I guess in particular what I'd like to know is what goes into Y in that last line. So a show of hands when you think you know. Okay. Someone want to tell me? How about you?
It's a value stored in memory address hex 40.
Exactly. It may be garbage. So what gets stored into Y in this program is whatever is at hex address 20, which happens to be the first of 64 I/O registers. So if you have a peripheral device attached to this thing that is mapped to that address and responds to being written to, then you've just done something with a peripheral device. You wrote a value. Wait a minute. No, you read from it. You read from it. So maybe your A to D converter, right, gives you the reading of its last conversion in that memory map location, and you just loaded that reading into variable Y. Yes? Right, because it's an 8-bit processor. So the fact that it's an 8-bit processor in this case really means that each address refers to 1 byte, and you operate on bytes at a time. Okay, so in summary, the 8-bit quantity in the I/O register at location 20 is loaded into Y. Okay, so here's another question. Where are X, Y, and Z in memory? And again, let's do the same exercise. So your choices are statically allocated by the compiler, on the stack, or on the heap. And while we're at it, figure out how much memory is associated with each one. Right? Hopefully you can. So a show of hands when you think you got it. Okay, that's pretty good. So how about, can you tell us?
So these are the static memory and Y are on the stack.
Right. And how big are they?
So X is 16 bits address, Y is 8 bits, and
Perfect. Good. Okay. All right. How about this one? So here's the first use of the ampersand. So what I guess in this case, what I'd like to know is, what does the last line do? Sorry? Yeah. Yes.
There's rewriting hex code 20 to random place. The random place depends on the initial value that the compiler allocates for one.
No, not quite. Not quite. So let's look at this. Okay, let's look at this carefully. All right. So X and Y are both going to be on the stack. X will be given 16 bits, or 2 bytes on the stack. Y will be given 1 byte. Okay? The second line takes whatever address the Y variable was given on the stack and loads it into X. X can store 16 bits, so it can store the address. Okay? Then the last line writes to that address the value 0x20. Okay? So this is a very arcane way of saying y equals 0x20. That would be an equivalent C program. Okay? Notice that because C allows you to find out what the addresses are of things on the stack, you can write some pretty nasty procedures. You can, for example, find out where the program counter was stored when this procedure was called, and then overwrite that value. So you can write a procedure that when it returns, doesn't return to the same location from where it was called. By the way, that's how an operating system does multitasking. Okay? Because you will call a procedure, and then you may not want to return to the same place. You may want to return to a different place to resume some other task. Okay. What goes into Z in this program? Okay, so again, let's do this the same way. So a show of hands when you think you know. I've only got one hand. I guess there's a lot of lines in this program, so that's fair. Okay, it can take a few minutes. One thing that I might help you with is, if you don't recognize uint16 underscore t, there's a whole family of data types that were added to C later because people realized that it wasn't a good idea to have ill-defined or only half-defined data types. Okay, int is not a fully defined data type. So uint means unsigned 16-bit integer, and underscore t just means it's a type. Okay, so show of hands. I'm getting more hands. Okay, good. So let's hear from someone I haven't heard from yet. I have heard from everyone who has a hand up. Just about, I think. Maybe not you.
You will contain the value that whatever value was stored at position or address 0x20.
Right. Exactly. So Z, this does the same thing as the previous program. Okay. It's reading from this I/O register at 0x20 and loading it into Z. Okay? Yeah. It compiled on my C compiler, but that was a couple of years ago that I tried it, so it may not anymore. I don't know. You're right. I mean, it's a nasty program because it's misusing the data types. All right. The big one. Okay? find the flaw in this program. How about a show of hands when you think you know what's wrong with this program? Okay, cool. How about, you want to tell me back there?
So what happens is that you no longer get the value stored in Z because when foo returns that memory is no longer on the stack moves up. So when you dereference, when you get the initial result equals foo, can you make it what you had, but you may get something else?
Right. This is a really nasty, insidious kind of programming error because the odds are when you test this program, it's going to work fine. Okay? You're going to get a result, and you're going to use the result a few lines later, and it's going to be the result. Okay? And you're going to think your program is correct. But it's not. And the program is actually extremely vulnerable. And in particular, one of the things that could happen is between the time you assign this result to this variable and the time that you use it, an interrupt might occur due to a timer or an I/O device, and a whole bunch of stuff will get pushed on the stack because a bunch of procedures will get called, and the result will get overwritten with some random value, and then when you go and read the result, it'll be something quite else from what you expected. Okay? So this kind of insidious error these are the kinds of errors to really watch for. It's not enough to just test your program and see that it did what you expected. Okay? That's not the way you build confidence in embedded systems, and no one will ever let you deploy a safety critical system just because it worked in your tests. Okay? You really have to analyze the code. And in this case, the code has a very serious flaw, and it's particularly serious because your program will almost certainly work correctly when you test it. Yes? Right. Well, yeah, or we could just... there's a bunch of things you could do to fix this, right? I mean, a return value is preserved as the stack gets dereferenced. So probably the right thing to do is instead of returning the address of the result, just return the result, right? It's probably what you should have done. Okay. So here's the analysis. This is a statically allocated memory location. The argument goes on the stack. This variable gets allocated on the stack. When the procedure gets called, the argument 10 goes on the stack, Z goes on the stack, possibly other stuff might go on the stack, the program counter. And the procedure foo then returns a pointer to a variable on the stack. And that's not generally a good idea because by the time that procedure has returned, the stack pointer has deallocated that location, which means it's now free to be used by anything else. Another procedure call, an interrupt, anything else. Okay? All right. So for this program, what do you think the final value of Z is after this call? So Z is getting initialized to 0x1. Z is a static variable. Z is not referred to in foo. So it seems obvious, right? Z after this call should have value 0x10. Will it? Yeah, so someone want to give me an explanation of what happens in this case? Yes. So the numbers here are actually carefully chosen so that you will get a stack overflow, no matter how frugal your compiler is, right? No matter how little it manages to use the stack, There's enough stuff that has to go on the stack that you will get a stack overflow. In fact, it'll overflow quite badly. It'll not only overwrite your statically allocated value of z, okay, but it'll also start writing into these I.O. registers and into your registers, so there may not even be an after foo gets executed because your program counter will get some random value, and you're going to jump to some random location and start executing garbage code. Okay? Yes? No, because, so I first call it with 0x4ff, which is certainly greater than 0x100. And then I decrement the argument by 1. So the second call to foo will have 04fe as the argument. The third call will have 04fd, and it'll just keep calling recursively. And each time it calls, it at least pushes the program counter onto the stack, and a byte for y. Okay? So the program counter will take 2 bytes. The byte for y will take 1 byte. So on each call, it's going to at least increment, or decrement in this case, the stack pointer by 3. Okay? And there's enough calls in there to walk through this entire memory. Yes? The recursion doesn't even have a return value here, right? So I don't think the compiler can do much with it because the only reason for this call would be because of its side effects. Yeah. Yeah. So let me just close this with one comment about the heap. I haven't said anything about the heap, and there's a good reason for that, right? So the heap is just it's a chunk of memory that you can use, that the program can use sort of dynamically. So it temporarily allocates a location to a variable and then deallocates it. This requires a supervisory procedure. So it means that your runtime system is going to have a table of information about what has been allocated in memory and what is free, okay? And it has to provide it, your runtime environment has to provide a procedure for allocating memory and a procedure for deallocating it. And in C, these are normally called malloc and free, okay? Those are the two procedures you call. Those are usually part of an operating system. But in an embedded system context, often you have a very small runtime kernel, and the runtime kernel may only provide malloc and free and nothing else, okay? It can be that small, all right? So there's other issues. I'll talk a little bit next time about caches, but not too much because I'm going to mostly count on you reading about them in the book, but we'll spend a little bit of time on them next time. And let's stop there now because we're out of time.